So the place where we stopped in the last class was a discussion on first order systems, right? And the general governing equation of a first order system is given by this: t times dy dt plus y of t is equal to u of t, right? Where t is a real number in general. Of course, please recall where we were. So we are looking at two aspects. So in any control design, there are two aspects which we had to look at. The first one was on stability. The second one is on performance, right? So of course, only when the system is stable, we can talk about performance. That's something which we discussed previously. So we looked at what is called as bounded input, bounded output stability. Now we are looking at performance. Okay, that's where we are, right? So as far as performance is concerned, we want to essentially obtain some quantifiable parameters, that can be used to evaluate a system's response, right? That's our objective. So, so as far as stability is concerned, please note that this system has a pole at minus 1 over capital T. So we can immediately see that system is stable if capital T is greater than 0, right? So that's what we have. Now I think as where we stopped last class, what I asked you to do was essentially to derive expressions for the unit step response, unit ramp response, and unit impulse response, right, for this class of systems, right? So let's continue from there. So if you look at the unit impulse response, okay, let me start with the unit impulse response to begin with. So the unit impulse response means u of t is the unit impulse input. So consequently u of s is 1, right? So immediately y of s is equal to p of s times u of s, which will just be 1 by ts plus 1. Okay, and how can I simplify this? I can rewrite this as 1 by t times s plus 1 by t, so that we can essentially get the form as 1 divided by s plus a, right? So if we get this, we immediately observe that y of t is going to be equal to 1 by t e power minus capital T by t, right? So that's the unit impulse response, right? So if we want to plot this, see, whenever we want to calculate all these responses, of course, I'm sure by now you would have got what is the general process. You use a system transfer function and the corresponding input, take inverse Laplace transform, get the function in the time domain, and also typically we comment on the output also, right? We can immediately see that for capital T greater than 0, what will happen as t grows to infinity? Y of t goes to 0, right? So that's something which we can immediately observe. And what happens at t equals 0? Of course, the initial condition should be 0, but please note that we are giving an impulse input, right? So that the impulse input, an ideal impulse, is almost instantaneously going to a very high magnitude at t equals 0 and coming back once again, right? So given that, you see that the output is discontinuous at t equals 0. It increases from 0 to capital 1 over t. That's how it should be interpreted, right? Please remember, the assumption that we made while deriving transfer function was that all initial conditions are 0 to begin with. So the unit impulse response of a first order system that we are considering is that it increases from 0 to 1 by t, capital T, almost instantaneously. And then once it reaches capital 1 by t, it decays exponentially, right? With the exponent being minus 1 over capital T. Okay, that's the interpretation here. Okay, so this goes to 0 as t tends to infinity. Okay, so this is the unit impulse response. Okay, now let's calculate the unit step response. So unit step response means u of t is going to be equal to 1, u of s is going to be equal to 1 divided by s. So this implies that y of s, which is p of s times u of s, is going to be equal to 1 divided by s times ds plus 1. Okay, and how can I rewrite this? So if I want to do partial fraction expansion, I just rewrite it as a by s plus b by ts plus 1. What will be a? I think from here onwards we will just directly start writing the residues, right? Yeah. So a is going to be just 1, right? You multiply both sides by s, substitute s equals 0, right? So we are going to have 1, and b you multiply both sides by ts plus 1 and substitute the root of ts plus 1. That's going to be s equals 1 minus 1 over capital T. And once we do that, what we are going to get? We are going to get minus capital T as b, right? So this is going to come as minus t as t divided by ts plus 1. So this I can rewrite as 1 by s minus 1 divided by s plus 1 over t, right? So if I take the inverse Laplace transform of this, what am I going to obtain? So I will get y of t to be equal to 1 minus e power minus t by capital T. Okay, so this is something which I will get. So immediately, you know, like we can plot y of t versus t, and what can you say about the output function plot? So what's going to happen as t tends to infinity? The value will approach 1, right? So it will go to 1 asymptotically, right? See, the word asymptotically is used in the sense that what happens as t tends to infinity. Okay, so that's what we are interested in. So the initial value is 0, as you can readily observe, and what's going to be the profile of y of t? It's going to increase from 0 and just go to 1 as t tends to infinity. Okay, so that's the unit step response. Okay, so there are a few observations that one could make from the unit step response. Immediately we can observe that at t equals capital T, y of t is going to be equal to 1 minus e power minus 1. And can you calculate and tell me what is 1 minus e power minus 1? Point? Please do the calculation and tell me. Yeah. Yeah. If you have a calculator, no, please calculate. So let's see whether we have a calculator here. I'm sorry? 0.632, right? So that's what it will come to as, right? So this will come as 0.632, right? And 0.632 is nothing but 63.2% of 1, right? Which is the steady state output, right? So this is the steady state value of the output function, right? So 0.632 is 63.2% of 1. So essentially, if we take t equals capital T, what happens is that this value reaches 0.632. Essentially, that's the way in which the parameter t is defined. The parameter t is what is called as time constant. It is defined as the time after which or at which the output magnitude is 63.2% of its final steady state value. Okay, steady state value. Of course, what goes without saying is that, like, for a stable first order linear time invariant system, right? So because that's a system we are analyzing, right? See, I don't want to keep on writing the same thing again and again, right? Our premise is that we are dealing with a stable first order LTI system, right? Causal system. So for that class of system, the parameter capital T is what is called as time constant, and its definition is this. right? It's defined as the time at which the output magnitude becomes 63.2% of its final steady state value, right? Steady state value, right? So that is the definition of time constant, right? So we will see that this time constant is the single most parameter that is important for characterizing the first order system dynamics, okay, dynamic characteristics, okay, like so we'll see what happens. Right now we can immediately observe that at time t equals capital 4t, the value of the output is going to be 1 minus e power minus 4, right? And can you calculate and tell me what is 1 minus e power minus 4? I think I'm doing something wrong here. Sorry?
0.981.
Okay. Yeah, here it is. So 4 minus, oh sorry. Just see minus 4. Okay, if you take exponential, that's what you have. And then like if I do minus 1, so essentially you take positive of this, so we are going to get 0.98, right? 0.982 or something like that, right? So essentially it's going to be 0. Close to 0.982, right? Do you agree? 0.981 something, right? So this is like 98, close to 98% of the final value, right? So what happens is that as I go to a time which is 4 times capital T, the output value becomes almost, this value is around 0.98, okay, which is essentially 98% of the final value, right? And why is this important? Because if I want to evaluate how fast is the system, right? So let's say if there are 60 of us in this class, right? We design 60 first order systems. So all of us know that if we design stable first order systems, the output will go to the final value as t tends to infinity, right? But I need a finite number to compare 60 designs, right? So then, what we do is that we draw a band around the final value, which can be typically taken as plus or minus 2% by convention, okay, or one could say plus or minus 5%, okay, like you will see that people will use different bands, okay, around the final value to quantify the speed of response. So if I say plus or minus 2%, so in this particular case I am dealing with the question as to when the output will come to 98% of the final value, right? And that happens to be 4 times the time constant, and this parameter is what is called as the settling time, okay. So settling time for a first order system, we are asking the question is that like what is the time taken for the output magnitude to settle within 2% of its final value, okay. So that's the question that we are asking. Of course, see, all these parameters are defined based on the unit step response, okay. Please remember that, okay. That's why I mentioned that many response parameters are defined based on the unit step response, okay. So if you want to evaluate, if I give you an experimental system and I ask you to find whether first of all the system can be approximated as a first order system and then evaluate time constant, step, settling time and all, you have to use the step as the input, okay. So please remember that you need not use unit step all the time, okay. That's why I am writing as percentages, right. So if you give a unit step, if the transfer function happens to be in this structure, you will get 1 as the steady state value, but we will shortly see that that need not be the case all the time, okay. So because we are dealing with linear systems, right, I can always scale the input and the output, doesn't matter, right. Yeah. So settling time, that is the definition of settling time, okay. So one can immediately observe that the time constant capital T is a very important parameter for us, right? So essentially that quantifies, how fast is my system response, right? So and dynamically, it's of great use to us when we deal with characterizing the speed of response. That's why we would typically encounters questions like, oh, what is the time constant of the system, right? When someone wants to talk about the speed of response of a system, let's say it doesn't matter whether it's an actuator or a sensor and so on, right? So people, when someone asks you that question, it is implicit that they are already considering or visualizing that system as a stable first order LTA system, okay, because that's where this parameter makes sense. Okay, fine, yeah.
So choosing 4t, does it have to be an integral value? That is 4.
Not necessarily, that's by convention, right? So at capital 4, the settling time definition is typically taken to be within 2%. So you see that at 4 times capital T, you settle with at around 0.981. So we're not exactly taking it.
As a value of 3.99p, you may get more accurately 98.
98%, but this is just a convention, okay? Just taking a round number, that's it, okay? Yeah. Fine, yeah. So, but certainly you can see that at 4 times capital T, I have settled within 2%. Okay, 98.2% is within 2%, right? So, in fact, we will see that interestingly, this raises a very interesting generic question. Okay, we are going to look at how we can convert all these performance specifications into something which we can work with, as far as control design is concerned. We will see that it's very likely that it's going to be tough for us to meet equality constraints. Okay, there is, we don't want in practice, we always like inequalities to work with, because so that we have a range. If you give me an equality constraint, yes, mathematically it's nice to write an equation, right? But practically you will see that you will be constrained a lot. Okay, we'll discuss this point later. Okay, so that's why we are saying within 2%. Okay, and we are happy that 4 times capital T is a good measure of settling time. Okay, yeah. So now let's go and look at the unit ramp response. Okay. So unit ramp response means U of t is capital T, U of s is 1 by s squared. See, by the way, all of you should know this terminology by now, right? So see, in your quizzes and exams, I am not always going to draw block diagrams and write mathematical functions. Many times I will use English words, right? So then you need to interpret from those English terms, what I am asking for. See, for example, if I say design a unity negative feedback, you should already know what that means, right? So if I ask you to calculate the unit step response, you should know what U of t is. I won't give you, okay, calculate Y of t when U of t is 1, right? So I may ask you in practical terms, right? So essentially, please remember these terms, okay, and what their meanings are. Okay, so unit ramp response means, U of t is t, U of s is 1 over s squared. So Y of s is going to be equal to P of s times U of s. So that's going to be 1 divided by s squared times ts plus 1. So what is the partial fraction expansion of such a factor? A divided by s plus b divided by s squared plus c divided by ts plus 1. And what can you calculate? So what are the values of a, b and c? A equals minus t, okay, b 1, c plus t squared or minus t squared? Is it okay? So how did we calculate? Let's go from c, okay. If I want to calculate c, multiply both sides by ts plus 1. Substitute the root of ts plus 1, this is minus 1 over capital T. So if you essentially multiply by ts plus 1, this ts plus 1 goes away, you are just left with 1 over s squared on the left hand side. That essentially works out to be capital T squared, right? So that will be c. Of course, you can find b readily because you multiply both sides by s squared, substitute s equals 0, you will get 1. For finding a, you will substitute any other value of s. See, we have used 0 and minus 1 over capital T, right? You can use plus 1 over capital T or 1 or 2, whatever other value of s that you can think of, and I am sure you will get a to be minus capital T. Am I correct? Right? So, if I take the inverse Laplace transform, for a few classes now we have been doing this residue calculation very carefully, right? From today onwards I will just we will discuss and write down the final values. By now I expect that you will be familiar with the process followed, right? So till date, if you look at all the examples that I did, I carefully wrote down each and every step, right? So kindly refer to the notes which have already been posted online, right? So keep on doing those problems, okay? Then you will get the practice. So if we do this, so what we are going to get? We are going to get minus capital T plus small t plus t times e power minus t by capital T. How did this become t e power minus t by capital T? Because this I can rewrite as t divided by s plus 1 over t, right? So this becomes this. So essentially what I get is the following, we get t minus capital T times 1 minus e power minus capital T. Okay, so that's what we get, right? So how is this response going to be? So you see that if I give a unit ramp input, that means u of t is t. So my function u of t is t, okay, right? So the ramp response is going to be something like this. So I am drawing an exaggerated diagram just to convey the point, okay, right? Okay. So you immediately see that as t tends to infinity, what happens to y of t in this particular case? Goes to infinity, but what function does it tend to? It becomes t minus capital T, right? Of course, the magnitude goes to infinity, I do agree, but the functional form goes like t minus capital T. So what I mean to say is that if you take a time which is high enough, so the gap between the function t, which is your input, and the output is going to be capital T graphically. Is it clear? Right? So that was my intention, right? So that's what this analysis tells you, okay? So this is the unit ramp response. Please note that unit ramp is an unbounded signal, okay? Obviously, although the system is a stable one, please note Bibo stability means output should be bounded for all possible bounded inputs. Ramp is not a bounded input, okay? So please don't, we should not say, oh, how come the output is going to infinity in magnitude? Yes, it would, because the input is anyway not bounded, right? The input is going to infinity, right? As time t tends to infinity. So that's something which you should keep in mind. So this is the unit ramp response, okay? Now, if you look at all the three responses, like what can you observe? Let's say this is our unit ramp response, right? And we look at our unit step response, which is this in the red box, right? Can you find some correlation between them? Just from between the two functions, right? I'm sorry. Good. So essentially, of course, with a constant, you need to evaluate that constant. Conversely, you can say that the step response is the derivative of the ramp response. You take the time derivative of the ramp response, you get the step response. And now you take the time derivative of the ramp input, what do you get? 1, right? You take the derivative of the unit ramp input, which is t, small t. Obviously, we are going to get the derivative as 1. So this is a very nice feature of stable LTI systems, right? So essentially, not only generally LTI systems, in the sense that you give an input u of t, you get an output y of t. You give an derivative of the input, you will get the derivative of the same output. Okay, so that's another nice property of linear time invariant system, the class of systems that we are studying. Okay, so let me just write down whatever I just said, so one can observe then. If you have an LTI system, right, so you give u of t and you get y of t. Okay, this implies that to the same system, right, you give du dt, which we get dy dt. Okay.